Okay, so thanks very much. Okay, so I'll continue with my lectures on Cartan geometries. And so basically, yesterday's talk, apart from the generalities of the concept, was mainly devoted to the example of the Cartan description of conformal structures and of conformal geometry. And this looked very spatial somehow. So we used compatible principal connections and tautological forms, and this looked very specific. And so the first step in today's talk will be getting a general perspective, or digging out the algebraic core of the construction in the conformal case. Okay, and this leads to a general procedure for constructions of canonical Cartan connections. And as you can imagine from yesterday's lecture, this generalization is in a way surprising because it doesn't start from the structure that you want to describe, but it starts from the homogeneous model. Yeah, so what you actually get is you get a large class of families of homogeneous models, which give rise to Cartan geometries that share properties with conformal structures. And fortunately, this family contains a large number of very interesting examples that were even studied before independently. And this is the class of parabolic geometries. And I'll also briefly discuss a further generalization to cases in which you get Cartan geometries associated to filtered versions of G structures. I mean, this is true for all parabolic geometries, but the parabolic case is a rather specific setting, and I'll discuss generalizations. Yeah, I should say I just want to give you an impression what this looks like. Yeah, so I will not be precise in all details, and there are some, well, lots of technical points that I'll just move over. Yeah, so don't take everything I say up to the last epsilon. It will not be true up to the last epsilon. But I guess I hope to convey the right picture here. Okay, yeah, and in the second part of this talk, I will discuss Cartan geometry methods, starting with geometrical methods, mainly relating Cartan geometries of different types. And again, I will focus, as I announced yesterday already, I will focus on cases that are either related to conformal geometry or to the geometric theory of differential equations, to be close to the topic of this workshop, to the topics of this workshop. Okay, yeah. So the first general methods or class of general methods that I will discuss is constructions relating geometries of different types. And then I will discuss a bit about constructions for invariant differential operators. Okay, so let's get started with the general perspective on construction of Cartan geometries. And this, as I said, this leads to parabolic geometries and their generalizations. So if, as I already said, the construction of the conformal Cartan connection that we did yesterday looked rather specific. Yeah, so we started with compatible connections. We attached to each point in a principal bundle the space of all torsion-free connections. So we put quite a bit of effort into the construction of the Cartan bundle and got the tautological form and so on and so forth. But if you look at these things from a general perspective, you find out that some things have to be actually quite simple. Because, for example, we were talking about these P plus, which was what I called the higher order part yesterday. Yeah, so these correspond to automorphisms that fix a point to first order, but not to second order. And we said this is isomorphic to Rn, so it's a contractible space. And if you look at the Cartan bundle as a bundle over the conformal structure you start with, it's a principal bundle with that group, but any principal bundle with a contractible structure group is trivial. Yeah, so in a way, it's pointless to put effort into the construction of the Cartan bundle because in the end it has to be trivial over the conformal structure. Okay, and this is the basic spirit that we will follow here, and we will replace these geometric constructions by more brute force constructions using algebraic input, in a way, if you want to put it like that. Okay, and second point, I already mentioned that also. If you're trying to generalize from the conformal case, then you should start by generalizing the homogeneous model and not the geometric structure. Again, this is not a complete surprise, because there were old results by Kobayashi and Nagano classifying geometric structures with non-trivial first prolongation, but of finite type, and they immediately lead to simple Lie algebras. Yeah, so these structures are mainly well understood because their classification corresponds to the classification of Hermitian symmetric spaces. But already there, yeah, the main thing is the Lie algebra of the automorphism group. That's the thing where you get the information and not the structure itself. Yeah, there is a uniform description in terms of homogeneous models and not the uniform description in terms of geometric structures. Okay, and if you follow this spirit, then you can even go much further. So you can get to these geometric structures that correspond to Hermitian symmetric spaces, but actually it gets much more general. And the starting point of this is a more precise description of the conformal case from a Lie algebraic point of view. So as you know, we started for the homogeneous model from a Lorentzian group, from a Lorentz group. And so if you look at the Lie algebra of a Lorentz group, then this admits a very nice and simple decomposition of the form G is G minus 1 plus G0 plus G1, which is a Lie algebra grading. And so this G0 here is exactly, this corresponds to yesterday's notation. This is the Lie algebra of the conformal group. G minus 1 is Rn, G1 is Rn, so these are abelian subalgebras. And then there is a Lie bracket mapping G minus 1 times G1 to G0, which in a way is a central ingredient for conformal geometry. Yeah? So you have this decomposition, which defines a grading of the Lie algebra in the standard sense. If you take a bracket of an element of Gi with one of Gj, you land in Gi plus j, yeah, where all other components are 0. And this has the property that the non-negative part of this grading is the Lie algebra of the subgroup P. And even better, the positive part of this grading is the P plus, which encoded the higher order stuff. Okay, so the setup is very nicely encoded in terms of this grading. And now you can just forget the specific case, go to general semi-simple Lie algebras and general gradings of that type. Okay, and it turns out that if you do such gradings, yeah, you will have to get, they will always be symmetric. So they will start at minus k and go to k for some integer k. Yeah, and then it turns out that the classification of such gradings up to isomorphism corresponds to the classification of parabolic subalgebras in semi-simple Lie algebras. And the correspondence is again exactly the same. The non-negative part of the grading is the parabolic subalgebra. Okay, and these parabolic subalgebras are very closely tied to the structure theory of semi-simple Lie algebras. Yeah, the classification is very simple. You just, yeah, semi-simple Lie algebra means roots. Roots reduced to simple roots, and the parabolic is uniquely determined by a set of simple roots. Yeah, you just pick some of these simple roots, they give you a parabolic subalgebra, they give you such a grading. You get an overview of all possible cases immediately. Okay, so this is a very well understood class of Lie algebras and subalgebras. Okay, right. So why do the conformal things generalize? If you remember yesterday's talk, The crucial ingredient that went into this story about the conformal Cartan connection was related to the study of the algebraic prolongations of the conformal Lie algebra. Yeah, I told you, you show that the first prolongation is n-dimensional. This gives you an n-dimensional family of compatible torsion-free connections. And the second prolongation vanishes. This gives you the hope to get a Cartan connection. And this is what enters the construction of the canonical Cartan connection. Yeah? And now, in fact, these admit a very nice interpretation in this Lie theory language. But since in the conformal case, we are dealing with abelian Lie algebras, yeah, it looks almost trivial. It just boils down to linear algebra. But what this does is, okay, this negative part here is a sub-algebra, just by the grading property. It's always nilpotent, again, by the grading property. And it acts on G by the restriction of the adjoint representation. Yeah, there's nothing deep about that. But then it turns out, yeah, if you have a Lie algebra, you have a module, you can form cohomology. Yeah, and while there's no nice interpretation about what this cohomology would mean here, in particular, note the higher degree cohomology groups, all these computations about prolongations can be rephrased in terms of a Lie algebra cohomology group. Okay? In the conformal case. And now there is an analog for general gradings. You have this Lie algebra cohomology, and tada, there is a way to compute this Lie algebra cohomology. And again, this is a very surprising result because initially, yeah, this computes the cohomology in a very general setting, and it's a theorem by Bertram Costand. And actually, it computes a cohomology that originally, if you look at it naively from an algebraic point of view, you don't know what to do with it. Yeah, nobody knows what higher Lie algebra cohomology is really good for. Yeah, but in this case, it was known that understanding these cohomology groups in this general situation gives you an alternative proof of what is called the Bott-Borel-Weil theorem, which computes sheaf cohomology of sheaves of holomorphic sections of homogeneous vector bundles on generalized flag varieties. Yeah, and if you look at the names that pop up there, Bott, Borel, Weil, and so on, it's a deep thing. Okay, and this boils down to this rather simple algebraic thing. Yeah, this is linear maps between finite dimensional vector spaces, compute their kernels, compute their images. Yeah, but in fact, if you look at Costand, even to understand the result beyond the dimension, you need representation theory. Yeah, the good description of these cohomology groups, they are really complicated, yeah, but they admit a great description in terms of representation theory of G0. Yeah, and this is the key information that comes from algebra here. Okay? Right, and all these facts are not restricted to the conformal case. You get them immediately for all these parabolic pairs. Okay, this was one essential ingredient. The second essential ingredient I tried to point out, although it's not so easily visible in the conformal case, was this issue about normalizing Cartan connections. Yeah? For the conformal case, this was exactly the torsion freeness on the one hand, which we took for granted because we knew it in advance, and this vanishing of the rigid type contraction that made the Cartan connection finally canonical. Yeah? Finding analogs of this description is again, it's just a linear algebra or representation theory problem, but this is the most complicated step in a way whenever you want to construct canonical Cartan connections. And again, this is very closely related to this Lie algebra cohomology of G minus with coefficients in G, this time to the second cohomology. Yeah, so somehow this cohomology or the Lie algebra differential that shows up here shows up if you try to compute the change of curvature of a Cartan connection from the change of the connection. Yeah, so Cartan connections form an affine space, and if you change your mind about the connection, you can check how the curvature changes. And this naturally brings up such a Lie algebra cohomology differential. Okay, and anyway, what happens is that for these semi-simple cases, also Costand has done all the work for you. Yeah, because there is an operator that is traditionally called the Costand codifferential, which actually admits a simple interpretation as a Lie algebra homology differential. It provides such a normalization condition. Yeah, you just take the kernel of, or being in the kernel of the Costand codifferential as the normalization condition. Okay? And so the two important ingredients that are needed in the end for constructing of the conformal Cartan connection are there in the general situation. And then, skipping over quite a bit of detail, you can run a general procedure to construct canonical Cartan connections for all these pairs G and P along the following lines. Okay, yeah, I should first say, okay, construct canonical Cartan connections from what? Yeah, and again, you can understand this in a way that is parallel to what happened in the conformal case. Namely, if you assume that you have a general pair GP, yeah, general here means semi-simple and parabolic. Yeah, so general in the context that we are currently talking about. Then if you start with a Cartan geometry of that type, this determines an underlying structure, more or less exactly in the same way as we did in the conformal case. You factor by the group P plus. Okay, so you take this bundle G, this is a principal P bundle. So in particular, you can factorize by the action of P plus, and you get a principal bundle G0 with structure group P mod P plus. And again, this is something which is very well understood from the theory of parabolics. This is always a reductive group, so its representations are easy to understand. Okay, and then you look at in the conformal case, this was very easy. The Cartan connection directly induced a strictly horizontal Rn valued one form, which gave us the underlying G structure. Here, this is a bit more. What happens? How is P plus defined in this general setting? If you start from the grading, P plus is the positive part. If you think about structure theory, it's the nil radical of the parabolic. Okay, right. Yeah. So in this case, your omega again descends to this quotient bundle, but the object it descends to is more complicated. Yeah, these are partially defined differential forms, and making this precise is quite a bit of work. But anyway, it admits an interpretation as a filtered analog of a G structure. So what should you think about? So what is meant by a filtered analog? So you look at a manifold, which comes with some additional data, namely smooth subbundles in the tangent bundle. Okay. You need a bit more. You need specific descriptions of integrability or non-integrability of these subbundles. It's actually non-integrability that matters. The example you should keep in mind is a contact structure. You have a manifold of odd dimension. You have a hyperplane bundle, and this hyperplane bundle is required to be maximally non-integrable. Yeah? Being maximally non-integrable means, in a vague way, looking like a Heisenberg algebra. Yeah? It's not true on the level of the tangent bundle, it's true on the level of the associated gradient of the tangent bundle, but I don't want to go into these details. Yeah? So you have subbundles, you have prescribed non-integrability properties of these subbundles. And then such a thing has a canonical frame bundle, and you can look at reductions of structure group of this canonical frame bundle. This is what I mean by a filtered analog of a G structure. Okay? And we certainly don't need the details here. Okay? But let us start with a very nice example. This is just the complex, or if you want, the unitary version of conformal geometry. Okay, so instead of SO n plus 1, 1, you start with SU n plus 1, 1. Yeah, so this is a Lorentzian Hermitian form. Okay, this again has a null cone, but I don't feel able to draw it because already yesterday the dimensions were much too low. Yeah, so this acts on Cn plus 2, and in there is a null cone consisting of complex lines. And if you projectivize this null cone, then you find out that this space of null lines again happens to be a sphere. This time a sphere of odd dimension because it's a unit sphere in a complex vector space. Okay, and this sphere, okay, if you look at this at each tangent space, this is a real hyperplane in Cn plus so if you take S to A plus 1 as the unit sphere in Cn plus 1, each tangent space is a real hyperplane in Cn plus 1. This contains a maximally complex subspace. Yeah, so you get a hyperplane distribution, which happens to be a contact structure in this case. So this inherits a contact structure. And moreover, since these are the maximally complex subspaces, they are complex subspaces. So your contact structure is not a real vector bundle of rank 2n, but it's even a complex vector bundle of rank n. So it inherits a complex structure. Okay? And this is now exactly what the general filtered G structure looks like. Contact structure plus almost complex structure on the contact subbundle with a certain compatibility condition. Okay, so what you get is, yeah, this is the standard CR structure on the round sphere of odd dimension. And filtered G0 structures in this case are strictly pseudo-convex, partially integrable, almost CR structures. So in particular, whenever you have a smoothly bounded domain in Cn, or Cn plus 1, you look at its boundary, this canonically inherits such a structure under a small genericity condition. Yeah, if the domain is strictly pseudo-convex, then you will exactly get such a structure. Okay? So the question was what the non-integrability property is. It is that you deal with a contact structure. Yeah, you have a subbundle which is maximally non-integrable. Yeah, so it's the opposite of say taking a linear subspace, a real hyperplane in Cn. Yeah, then the corresponding subbundle will just be Cn minus 1, and this is integrable. And here you get a non-degeneracy condition that it should be maximally non-integrable. Okay? Okay. G0 in this context is the conformally symplectic group. Yeah, so it's you take SUN and you take multiples of the identity and complex multiples of the identity. Okay? And you take the group generated by that. Yeah, so it's perfectly analogous to the real situation, just with this additional thing of the contact structure popping out. Again, this is easy to understand from linear algebra, but this would take us too far. Yeah, I just want to give you this example as something that you can keep in mind as a model example, and I'll return to it with one of our constructions. Okay? So, and yeah, so these are the underlying structures that you can hope to get a Cartan geometry from. Yeah, and indeed for CR structures, this was known before by a seminal article of Chern and Moser and earlier work of Tanaka and so on and so forth. But again, this was like in the spirit as we discussed the conformal Cartan connection, so it was very specific to CR geometry, yeah, and not seeing the general picture behind it. Okay, right. And now I just want to give you a flavor how this proof of existence and uniqueness of Cartan geometries from such an appropriate underlying structure looks like. So what you do is This argument that the Cartan bundle has to be trivial over G0, this is always true. Yeah, P plus is always contractible, so there cannot be anything interesting in the Cartan bundle itself. So what you do is you start with your underlying structure G0. Yeah, so this is a principal bundle with group G0 plus this complicated configuration of differential forms where we don't need details. Okay? Then you just stupidly extend structure group. Yeah, you just form the associated bundle with respect to the left multiplication of G0 on P. This is the obvious way how to enlarge the structure group of a principal bundle to a group containing the structure group as a subgroup. Okay? Then you start making choices, yeah, in order to endow this bundle with its extended structure group with a Cartan connection that induces the right given underlying structure. And if you allow yourself to make choices, this is completely trivial. Yeah, this is not something which is difficult, you just choose. Okay? So you choose a principal connection on I think this should say G0. And then you use this choice. Yeah, probably it's better to choose it on G. It doesn't matter. You make choices. Yeah, and using these choices, you define some Cartan connection omega hat on G, which induces this given underlying structure. Yeah, this is something that poses no difficulties. Okay? Right. But then you see, and this is again, comes out of the definition and is very similar to what you know for principal connections. If you look at Cartan connections with fixed underlying structure, they form an affine space, basically modeled on horizontal equivariant differential forms. Yeah, horizontal equivariant one forms, very similar to the principal case. And now there comes a technical trickery. There is a notion of homogeneity in this setting, which you can see from the grading that we started with. But making this precise is rather hard because it doesn't work for the grading. You have to pass to filtrations and things like that. But anyway, there is a notion of homogeneity for Cartan connections and for curvatures. Yeah, because the Cartan connection is a one form, the curvature is a two form. You always have a concept of homogeneity. And then I can get precise on what I said before. If you look at the change of curvature caused by a change of connection, this will be governed by a differential equation, yeah, unavoidably, because roughly speaking, the curvature is d omega plus bracket of omega with omega. Yeah, so it's a differential equation and it's nonlinear. But if you look at the lowest homogeneous component, then miraculously, this turns out, or not miraculously, but unavoidably, it turns out to be tensorial and linear. Yeah? And even better, it's not just any linear map, it's the Lie algebra cohomology differential that I was talking about. And now you can take properties that you understand about this Lie algebra cohomology, use this in pointwise constructions, or in constructions that essentially are pointwise. Okay, and if you do this, as I told you, we have a normalization condition by the Costand codifferential, and then you can start to normalize the Cartan connection you have chosen, homogeneity by homogeneity. And in each homogeneity, this just means solving a linear equation. It's no problem. Yeah? So you can just show that you can correct homogeneity by homogeneity, modify your Cartan connection towards a normal Cartan connection. Okay? Right. And once you finish this process, you have a normal Cartan connection which induces the right underlying structure. Okay? What is the notion of homogeneity again? It comes from the grading we started with, yeah, because we are looking at forms with values in the Lie algebra. So the grading of the Lie algebra enters there, but also there is the filtration of the tangent bundle, which also enters the story. Yeah, and it's the interplay between the two. And as I said, it gets a bit complicated because it's homogeneity with respect to a filtration and not with respect to a grading. And to carry this out technically is difficult, but the idea is easy. Okay? Right. So this is, how do I find it? There is a finite number of steps. If your grading is from -k to k, then there are k+1 steps, something like that. All right. Yeah, this finishes the existence part. Yeah, if I start with an underlying structure, I find a Cartan geometry inducing that structure whose connection satisfies this normalization condition. I'm done with existence. What about uniqueness? Uniqueness here is even nicer than it was before. Namely, you don't have to care about the construction. If you have two normal Cartan geometries with the same underlying structure, they are isomorphic. You don't have to care how it was constructed. If it was obtained in some different way, you always know it will coincide with this canonical thing, because, and this is the information on cohomology, on this first cohomology group, Lie algebra cohomology group, implies that if you have two normal Cartan connections that induce the same underlying structure, they are related by an automorphism covering the identity downstairs. Yeah, so this is the best uniqueness statement that you can hope for. I should say, and this is not true for all parabolic pairs. There are two exceptions that are very well understood because they are related to projective structures and to a contact analog of projective structures. Yeah, so there the underlying structure is a bit more complicated than for the other parabolic geometries, but still the core of the theory just goes through. Okay, so this is what I said here. So if you take parabolic geometries, except for these two examples, sorry. Then you get a categorical equivalence between these Cartan geometries, or I should say normal Cartan geometries, and the underlying structures. And as I was pointing out before already, you don't have to care about constructions anymore. Yeah. No, I can't. I mean, it's this filtered analog of a G structure. Yeah. In the case of CR, it's a CR structure, and I will list some other examples. Yeah. But the point is, describing these structures in a uniform fashion would need 15 minutes or something like that. Yeah. I mean, there is a uniform description if you have this algebra setup in mind, but it's complicated. Okay. Yeah. Yeah. The point is, for the uniqueness here, you don't need any reference to a specific construction. Yeah, this is a tricky issue if you construct the normal Cartan connection, say the conformal Cartan connection in the way we did yesterday. Yeah, if you then arrive at something by a different construction, it's hard to say whether they are the same because you somehow have to run through the procedure in order to get the connection. Yeah, whereas here you just get an abstract statement. If torsion-free and rigid type contraction vanishes, then these guys are isomorphic. Okay. All right. Yeah. Very briefly, there is a more general procedure, and there will be a reference in the end. So what you do here is you start with a homogeneous model. Now GP are arbitrary. What you need is you need a filtration on the Lie algebra, which is related in a nice way to P. And then this filtration also gives you a subgroup P+. And then if you do this, yeah, under these assumptions with this filtration business, then any Cartan geometry of type GP determines an underlying filtered G0 structure, where G0 is again the quotient by P mod P+. Yeah, and you can read this off from the algebraic data that you started from, what this structure will look like. Okay, and then what you can do is you can abstractly specify what you need in order to get a canonical Cartan connection. And what you need is all finite dimensional information. Yeah, you need information on the prolongation. Yeah, this is just verifying if you want, you can phrase it in terms of Lie algebra cohomology. So verifying facts about H1 of G minus and G. Yeah. And then you need this normalization condition, yeah, which is not easy to get. Yeah. And I mean, there are some general ideas on how you get it, but this is something that you have to do case by case. But if you provide this information, then there is a general procedure that constructs such a categorical equivalence. Yeah, then you have a procedure similarly to the one for parabolics, where you just use the ingredients. Yeah? So this is just grinding out the technical core of what we did before for a general procedure where you specify some input that is needed to deal with a specific case. One important application of this is that this input that we need here is provided for all the geometries describing ODEs up to contact transformations or systems of ODEs up to contact transformations. Yeah, and they are non-parabolic, so this goes far beyond the parabolic case. Okay. So now briefly, what are the underlying structures that are around for which this categorical equivalence has been established? Most of these examples are parabolic. So these are almost Grassmannian and almost quaternionic structures. So almost Grassmannian basically means you identify your tensor, your tangent bundle of your manifold as a tensor product of two auxiliary bundles. And almost quaternionic is, yeah, the underlying structure of quaternion Kähler manifolds. So, okay. Then there are classical projective structures in which you study the geodesics of connections, I would say. Yeah. So this means you have an equivalence class of connections where two connections are equivalent if they have the same geodesics up to parametrization. One of the interesting facts about this is that any Riemannian metric has an underlying projective structure, yeah, because it has a Levi-Civita connection, and this Levi-Civita connection has geodesics. And some interesting features of Riemannian geometry, for example, the Riemannian deformation complex, admit a projectively invariant description. So there are interesting relations to Riemannian geometry here. Okay, yeah, then there is path geometries, which is a classical concept where on a manifold you have given a family of unparametrized curves with one curve through each point in each direction, and they can be used to equivalently encode systems of second order ODE up to point transformations. So all these three cases are parabolic. Then there is this story about the ODEs that I was referring to. So if you have a single ODE of order at least 3, then this can be, so of fixed order at least 3, this can be geometrized up to contact transformations. And this is parabolic for order 3. This is going back to work of Chern. And it's non-parabolic for order at least 4. Then you have systems of ODEs of order at least 3. They are all non-parabolic. Then there are Legendrian contact structures, which are like a real analog of CR structures and are related to the geometry of Monge-Ampère type equations. Yeah, split quaternionic contact structures, in particular generic rank 4 distributions in dimension Z, which are closely related to instantons and stuff like that. And then there is a large family of generic distributions. So the 2, 3, 5 distributions that you may have heard of that go back to Cartan's 5 variables paper, and generic 3, 6 distributions, and generic, yeah, more generic distributions. Okay, so these are the examples of what the underlying structures look like. And you see, if you look it in the picture of the underlying structure, you won't see any system. Yeah, it's very diverse. Yeah, but the uniform stuff is they have a parabolic homogeneous model. Well, most of them have a parabolic homogeneous. Okay, so now let me come to the second part and let me sketch a few Cartan geometry methods. The main point I want to make here is, again, you can see everything from the homogeneous model. Yeah, if you have something interesting that works out for the homogeneous model, yeah, and this usually means, yeah, the homogeneous models have the flavor of linear algebra, basically. Yeah, because these are flag manifolds and stuff like that. Yeah, and so if you find interesting stuff for flag manifolds, chances are good that they carry over to do interesting things with the associated Cartan geometries. Okay, and the first example I want to discuss is exactly in this spirit, and these are called Fefferman type constructions. And here you start with CR geometry. Okay, and we got the homogeneous model as you take Cn plus 2, you endow it with a Hermitian, with a Lorentzian Hermitian form, you take the space of isotropic complex lines. Okay, but any isotropic complex line contains a sphere of isotropic real lines. And any isotropic real line spans an isotropic complex line. So what you see is that if you take the real isotropic lines, they form the total space of an S1 bundle over this CR sphere. Okay, and since this is a homogeneous vector bundle, it actually comes from a specific representation of the groups in question. So you can immediately get a corresponding S1 bundle by forming the corresponding associated bundle to the Cartan bundle over any CR manifold. Okay, and then you just do a bit of extension of structure group, and you read off that the total space of this S1 bundle inherits a Cartan geometry with group now SO 2n plus 2, 2. Yeah, and this means a Lorentzian conformal structure. Okay. Yeah, so whenever you have a CR structure, you can form the associated Cartan geometry, you form the associated bundle. Yeah, you get a sphere bundle. On the total space of this sphere bundle, you get a Lorentzian conformal structure. Okay. Yeah, and this is exactly what happens here. Now, there's an interesting question, and this wasn't even observed in these classical constructions. What I was describing was okay, start with the canonical Cartan geometry associated to the CR structure, hook up a Cartan geometry with the right group over the total space of a Cartan bundle, or of a sphere bundle over the underlying manifold. Question, is this the canonical Cartan geometry associated to this conformal structure? The answer is no in general. Yeah, it's not true if you start with an almost CR structure. It is exactly true if the underlying CR structure is integrable. And if you have this coincidence, then you get for free things like coincidences of canonical curves, which tells you that the chains of the CR structure are related to null geodesics of the associated conformal structure, and so on and so forth. Okay, so this is a very interesting construction from the Cartan point of view as well. Yeah, and actually things go further. So now you've got the construction of a special subclass of conformal structures. Start with a CR structure, form a circle bundle. This carries a canonical Lorentzian conformal structure. Can you characterize these things? Yes, you can, because what you came up with was the inclusion of SU into SO. And in fact, there is a notion of conformal holonomy, and you can characterize these conformal structures that you obtained in that way by the fact that their conformal holonomy is unitary. Or if you want, you can characterize them by the existence of a parallel complex structure on their standard tractor bundle. And things like that. Okay? Right, yeah, and this generalizes classical constructions. Fefferman did this for boundaries of strictly pseudo-convex domains. Burns, Diederich, and Schneider did it first for the Cartan connections provided by Chern and Moser. Yeah, so these are intensively studied in complex analysis. Okay, yeah, and you see, so here it boils down to the fact that SU is contained in SO. Yeah, this is the reason why this Fefferman construction is there. And if you look at it from that point of view, you find out many other inclusions between semi-simple Lie groups that form the basis of such constructions. And this is in the beginning of the next slide. So there are other inclusions of that type. For example, you can take the exceptional Lie algebra of type, or Lie group of type split G2, yeah, and this sits in SO34. Okay, so again, you have an SO group, you have split G2. It turns out that split G2 in this case gives rise to these generic 2-3-5 distributions that I was talking about before. Yeah, so maximally non-integrable rank 2 dimensions, rank 2 distributions on 5-dimensional manifolds. And for such, Pavel Nurovsky cooked up a construction of a conformal class. So his construction was a formula that covered the full page for one representative metric in this conformal class. And you can reduce this exactly to such a Fefferman type construction related to the inclusion of G2 into SO34. And similarly, there is an extension of a contact projective structure to a projective structure to the Daniel Fox. And in all these cases, you not only have the construction at hand, but you also get characterizations of the spatial structures that you obtain in this way. Yeah. Again, these 2-3-5 distributions, yeah, they give rise to a class of spatial conformal structures in dimension 5. And you can characterize these spatial conformal structures by the fact that their holonomy is contained in G2. Yeah, and if you go towards ambient matrix, this gives constructions of matrix in dimension 7 whose holonomy is contained in split G2 and things like that. Okay. Yeah, I think I'll skip over the next parts. Yeah, I'll skip over the next parts which describe generalizations of this. Ah, no, I shouldn't quite skip. Yeah. I skip over the generalization. There is a generalization of the Fefferman type constructions, which is called extension functors, in which even the homogeneous model can give rise to a non-flat geometry. And again, this gives interesting examples. What I want to say a bit more about is this issue of holonomy of Cartan connections. This was somehow, I mean, already Lie Cartan did a bit about that. And then it came up in conformal geometry around 2000. But somehow a major feature of holonomy of Cartan connections got missed in these discussions. And this was sorted out in a joint article with Roth-Gower and Matthias Hammerl a few years ago. And okay, this is very general theory of holonomy reductions for Cartan geometries. Okay, so you start with an arbitrary Cartan geometry, and naively speaking, a Cartan connection has no holonomy because it has no horizontal curves or anything like that. But it turns out that there is a way to extend a Cartan connection to a principal connection, and then you can look at the holonomy of that principal connection. And so in the case that your type is GP, your holonomy groups are subgroups of G. Yeah, so the conformal holonomy, as it was for the Fefferman spaces, is a subgroup of SON plus 1, 1, and not of the parabolic subgroup P. Yeah, so the holonomy groups are subgroups of the big group. And yeah, the simplest the simplest way to specify a subgroup in a group is to pick an element in a representation of this group and say you take the subgroup that leaves this element invariant. In geometric terms, this just means that you require some tractor bundle to have a parallel section. Yeah, because representation of the group G means associated bundle that is a tractor bundle, and to get a holonomy reduction, you need a parallel section of this tractor bundle. Yeah, so this gives the simplest examples of reduction of conformal holonomy, and it's exactly like, conformal standard tractors, put a parallel complex structure on this bundle. Yeah, or require that there is a parallel section in the complex standard tractor bundle, or a parallel subbundle of some dimension. Yeah, these are all examples that give rise to holonomy reductions. Okay. And now the interesting thing is, if you look at this subgroup of the group G, then this acts, of course, on the homogeneous space G mod P. Okay, and if you think about the simplest example, which corresponds to projective structure, so it didn't occur, but this is the simplest example of G mod P is projective space. Yeah, take G to be SLM plus 1, P to be the stabilizer of a line, you get projective space. Simplest example of a holonomy group would be some SOPQ in SLN. Okay? But then you see SOPQ doesn't act transitively on the space of lines, because on a line, your given inner product can be positive, negative, or null, or if you want, your line can be space-like, time-like, or light-like. So you see, this holonomy group acts on the homogeneous model, but the action isn't transitive, it has various orbits. And if you think about the example that I was giving about SOPQ acting on Rn, these orbits may have different dimensions, yeah, because the stabilizer of a light-like line is larger than the stabilizer of a non-degenerate line. So you have orbits of different dimensions. Oh yeah, this is exactly a more general version. If you start with SOPQ in SLN and the Grassmannian, then the orbits are determined by the restriction of the inner product to a subspace. Yeah? So there are several orbits, but you can understand them. Okay? Right. And now it turns out that in complete contrast to what happens for principal connections, a holonomy reduction of a Cartan connection in general gives you a decomposition of the underlying manifold. And this decomposition exactly corresponds to this decomposition of the homogeneous model, with not all parts being necessarily there, but whatever is there in curved geometries has to be there in the homogeneous model. Okay? So what happens is, if you have a holonomy reduction of a Cartan geometry to this structure group H, then the underlying manifold accordingly decomposes into what we call curved orbits, yeah, because these are just the curved analogs of the H orbits up there. And these curved orbits inherit Cartan geometries of different types because they live in different dimensions. And you can actually understand all these geometries and all these orbits from just looking at the homogeneous model. Yeah, because the types of Cartan geometries are obtained by looking at H and the intersection of H with appropriate subgroups conjugate to P. Yeah? So you just go through the list of orbits, yeah, and you go through the list of types, and you know on this orbit you get induced that, and so on and so forth. Okay, now this looks weird, yeah, but again, if you look at the simplest possible example, which is related to conformal geometry and a parallel standard tractor, and I'm phrasing it in a specific situation. In general, it would work with hypersurfaces or something like that. But what you can do is, if you take a manifold with boundary, then there is the concept of a Poincaré-Einstein metric on the interior of this manifold, which means that you have a negative Einstein metric on M that is conformally compact. Yeah, so it it gives you a conformal class called the conformal infinity on the boundary, and this is the picture that lies behind holography and stuff like that. Okay, so if you start with a Poincare-Einstein metric on M, then if you know things about tractors, a parallel section of the tractor bundle corresponds to an Einstein metric in the conformal class. So what actually happens is you get a conformal structure on all of M bar, and this conformal structure gets reduced holonomy. And the holonomy reduction, the two Cartan geometries that you get here, give you a Riemannian metric on M, which is the given Poincare-Einstein metric, and they give you a conformal class on the boundary, which is the conformal infinity. Yeah? So you have encoded the whole data in the interior and the data on the boundary into one object, which is the holonomy reduction, or which is the parallel section of the tractor bundle. Yes, in this case, the curved orbits are exactly the interior and the boundary, and the induced Cartan geometries are Riemannian. Yeah, and from normality, you can deduce that it has to be Einstein and a general conformal class on the boundary. And this is the basis of all these boundary calculi that Roth will talk about in his series of lectures. Okay, yeah, because this picture, I wanted to say this in the first talk, this not only works for Poincare-Einstein, but it also it extends to conformally compact matrix. Yeah, this will not be a holonomy reduction anymore, but you get corresponding data and so on and so forth. Yeah, and also there is a generalization to other types of geometric compactifications here. Okay, so I have very little time left. So I'll just say a few words about natural differential operators, because again, this is something where the Cartan geometry methods turned out to be very effective. Yeah, the motivating example here, of course, is conformally invariant differential operators, which were viewed kind of as a question of Riemannian geometry, because in Riemannian geometry, it's very easy to write out invariant operators since you have a Levi-Civita connection, and then you just check who remains unchanged under conformal rescalings. Yeah, and it turns out if you do this in order 1, it's a nice exercise. If you do it in order 2, it's a very hard exercise. And if you try to do it in higher order, in that way, you get lost. Yeah, so it took until the 80s since for writing out the square of the Laplacian in dimension 4 explicitly and stuff like that by such trial and error methods. Yeah, so if you do these direct methods, they get out of hand if the order gets a bit bigger. So what you're looking for is invariant constructions. Yeah, you try to do something which is conformally invariant from the outset, rather than checking whether things get independent of your choice. Okay, there are several indications why this is difficult. And again, this is something that holds for conformal geometry, but it actually extends to all parabolic geometries. If you look at the homogeneous model, then you just get what is called, you just get what is called G-invariant differential operators. Yeah, so if you have a homogeneous space, you form appropriate bundles. The group acts on the space of sections, and you're just looking for differential operators that intertwine this action. Yeah, and this is what representation theorists spend their life with. So there is quite a bit of information coming from representation theory. And the interesting thing that happens here is that for representation theorists, usually it's irrelevant whether this operator is differential or not. Yeah, they study intertwining operators, and if it's an integral operator, it's as good. Yeah, or fractional power of the Laplacian or something like that. But interestingly enough, there is a different branch of representation theory that directly tells you something about invariant differential operators. And this exactly applies in the parabolic case. and for irreducible bundles. So you have to look at irreducible representations of your parabolic subgroup P. And in this case, yeah, there is a correspondence between such operators and homomorphisms between generalized Verma modules. And generalized Verma modules is an interesting kind of stuff because these are infinite dimensional representations that can be treated like finite dimensional representations. Yeah, so they are countably generated, so you can work with them basically with linear algebra methods. Yeah, you don't need topology, you don't need continuity of linear maps and stuff like that. And what these tell you is, first of all, they tell you, I mean, representation theorists have sorted out what these homomorphisms of generalized Verma modules look like, not completely, but there's a lot known about those. So what this tells you are quite precise descriptions on the homogeneous model and strong restrictions in general, okay? So for example, what these things may tell you is, here's a specific bundle, there's exactly one conformally invariant operator acting on sections of this bundle, and this conformally invariant operator has order 17. Yeah. So if you try to construct this, you would like to write it somehow in terms of lower order operators. But there is no invariant lower order operator there as long as you stay in the realm of irreducible bundles. Therefore, you have to go to something more general, which is, for example, tractor bundles or the Cartan geometry methods. Yeah, you have to leave the geometric structures that you are used to, yeah, because there's nothing there. Yeah, you cannot hope to get some construction there. Okay, yeah, therefore you have to go to more general geometric objects which are provided by Cartan methods and tractor methods and things like that. Yeah, and I think before getting over time completely, I'll stop here and refer to the slides that will be up on the EASY web page soon for a glance on what such methods look like. Okay, so thank you very much. Yeah, and of course, you will get lots of examples in the lectures of Roth and of Michael Eastwood, and so there will be more on these issues.
Last part. Suppose you want to start from Laplacian and flat space to power k and extend it to more general geometry. Yeah. So then, okay, Laplacian to power k is fine, but then the dimension is not big enough, then it fails. So how you would detect all these abstractions and this algebraic language? What's the difference between different backgrounds?
Okay, so the point is this algebraic language talks only about the homogeneous model. So what this talks about in conformal geometry is conformally flat manifolds. On those you have all powers of the Laplacians without problems. Yeah? The methods I wanted to describe here, okay, so in that sense the question that comes naturally is, can you extend these operators to curved geometries, or even better, give a construction that applies to the homogeneous model and automatically works in curved situations. And all these constructions that are described in the remaining slides have this property. Yeah? But if you look at, if you try to construct powers of the Laplacian using these methods, it's getting complicated. Yeah? And you can exactly say where and why it fails. So the methods are different. Yeah, so there is no simple and uniform answer, but you can understand what's going on.
Any more questions?
Maybe I ask the question, how much do you construction depends maybe most of the
You mean whether you just have whether you really have a group G or just an Lie algebra G?
Yeah.
Nothing. Oh yeah, I mean it's very easy. Okay, so if you think, for example, about tractor bundles, yeah, I was saying, okay, take a representation of the group G and restrict it to P. You can equivalently say start from a Lie algebra G, comma P module. Things work out in exactly the same way. Yeah, so the group G is not a problem at all. If you have the Lie algebra G, everything that I was talking about goes through. If you drop the Lie algebra structure on G, this becomes a bit more complicated. Yeah? But again, quite a lot goes through, but it's not so easy to answer. Yeah? But otherwise, from between group G and Lie algebra G, there is absolutely no difference.